Alright, so today we'll be talking about antiderivatives and indefinite integration, which basically pretty much the same thing. So what it does is basically, all last semester we worked up to what is a derivative and how do we get there. And we were able to take something like this, such as f of x equals 5x to the fourth, and change it to f prime of x equals 20x to the third. Okay, and basically we just took the 4 and multiplied it by the 5 and then subtracted 1 from that. So we're going to ask ourselves, we're going to turn around this semester, how do we go backwards? D over dx equals 4x to the third is the derivative of what? Okay, so this is the derivative of what? So first off, we're going to use the connotation of when we get that specific function, we're going to use capital F of x. Okay, now if you notice, I multiplied by, if you notice on this one, when I went from top to bottom, I multiplied by the 4 and I subtracted 1. So when we go backwards, I need to add 1 to the exponent and divide by the number that's there. So in other words, I add 1 to here, get 4, and then okay, so basically, in other words, instead of going this direction, I'm going to go this direction. Now, we just talked about messing with it. Now, if you notice, I went down 1 exponent. I'm going to go up 1 exponent, and instead of multiplying, I'm going to divide. Okay? So in other words, if you notice, they kind of disappeared. I had a little bit of a hiccup with the computer system. Okay, so in other words, I'm going to divide 4 by 4 because that's the exponent up, and make this x to the fourth. Okay, and that's going to simplify to 1x to the fourth. Okay. All right. Now, if you notice, when I started with this original function, I didn't have a number that was all alone over here, and then it made it disappear to 0. Okay. So technically this should have had like a plus 0 or something. But here I started with nothing because this was my derivative, and I'm going back to the antiderivative. So I don't know what's over here. I could have had a 1. I could have had a 3. I could have had a 14. I could have had a minus 12. I could have had a minus 300. I could have had a pi. For all I know. I don't know what was over here. So to just, whenever you're doing indefinite integrals or antiderivatives, what you're going to do is you're going to add a c at the end. Okay, that stands for a constant that could have been there. Okay, so whenever you do integration, first off, change it from a regular f to a capital F, divide by the exponent that was before, and then move the exponent up 1. Okay, and that's the power rule for this. Okay, and also put the plus c. Now, if you don't put the plus c, I'm not going to be too happy. So when you're doing integrals, when you're going in this direction and you're getting an f, capital F of x, you should be having a plus c at the end. No matter what happens, have a plus c. Some books state a plus k. We're going to use a plus c for this book. So just so you understand, sometimes they'll change. It just stands for the constant. Okay? All right? Alright, now another way to actually write an indefinite or an integral or an antiderivative is to write with this sign. This is the integral sign. Okay, so in other words, if I have f of x dx, okay, this is going to equal capital F of x plus c. Okay. Alright, so here's my actual function right here. Now, this beginning part, it looks a lot like the summation sign, or in other words, the sigma from when we were doing sums back in Algebra 2, when you were working with infinite series or something like that. Okay, this was introduced by Leibniz, the father of modern calculus notation. Unlike most people think Newton had a different notation, but whatever. Okay, but the notation here, whatever's in between the s, the summation sign, and the dx, okay, that's what you do the integral on. Okay, right? So there's some very interesting things that actually work out with that. But what we're going to do is we're going to use this notation right here to do integrals from here on out. We call these integrals, these antiderivatives. We just call them integrals just for the sake of being. Okay? So some really cool stuff that you can actually do. Now I do want you to know that, like for example, if we had something like this, and if you're wondering how to get these signs, do Alt 244 for the top part and then Alt 245 for the bottom part. If I had 3x squared plus 5x minus 7, okay, and then I had the dx at the end, okay, I would actually go up one power, so this would be 3 divided by 3, x to the third, plus 5 divided by 2, x to the second, plus 7. This is technically 7 divided by 1, but we already know that that's going to be, you know, the x to the first. Okay, then we have our plus c at the end. Okay, so that one's pretty simple. Now, if I had my dx somewhere else, let's say I had the dx over here in front of the minus 7, I would still do the integrals on all of these. Oh, this should be plus. Sorry, that should have been a plus. That should have been a minus 7. I just realized that. Okay, I would still have the integrals on there, but then I would have my plus c here and then my minus 7 here. So wherever the dx stops is where I stop my integral. Okay, now if I had moved the integral over here to right here, okay, I would have left this as x. I would have moved everything over here. So this would have had the plus c and then the minus 5x minus 7. I wouldn't do anything with that because I'm not doing the integral on that. So whatever happens in between the summation sign and the dx sign, you actually do the integral on that. Now, you're probably wondering why we're calling this summation sign. We'll learn a little bit later when we're finding area why it's summation and where this actually comes from. So it's actually some really kind of cool stuff that works with it. Now, also, if you notice, the letters do match up. The x and the dx do match up. So if I was doing something like this, let's say I was doing let's say 4x dx. Obviously, this would be 4 divided by 2, so that would be 2x squared plus c. So that one's pretty simple. Now, if I had a different letter, let's just change that to, let's say, 4t dx. Okay, I would treat this as a constant. This 4t is a constant, and so I'd have 4tx plus c would actually be my answer. Okay, so there's some actually interesting things when working with this. You do have to pay attention to letters. It doesn't matter which letter you pick to be your, you could have dw and w here and just work that way. But when you're doing integral and you're using a different letter like dx on a t or dx on a w or something, you're going to treat that as a constant. Okay. Okay, so now what we're going to do is we're going to go to a website. This is mathisfun.com, and we're going to learn some of the rules for actually working with integrals, so integration rules. So when you have a constant, if you're doing the integral of a constant, notice how it's a different letter than right here. I do the same rule. It's going to be the constant times x plus c. They use a capital C, I use a smaller c. It's up to you how you want to use it. Okay, now the variable, if we have x dx, or the integration of x dx, it's going to be x squared over 2. Remember, it's the power above, and you're dividing it. Okay, all right, and this square, if you're doing the integral of a square dx, and you do need the dx to do the integral. If you don't have the dx, you're not going to be doing an integral. It's going to be x cubed over 3 plus c. Okay. Now, if you're doing the integral of a reciprocal, which is 1 over x dx, it's going to be the natural log of x. So do not just put a negative 1 and just work your way across. It's going to be the natural log of x plus c. All right, the integral of an exponent should probably make a lot of sense because the derivative of e to the x is e to the x. So obviously it's going to be that, but just have the plus c. Okay, exponential of a different base than e, a to the x dx, it's going to be a to the x divided by the natural log of a plus c. Alright, the integral of natural log of x dx is going to be the x times natural log of x minus x plus c. And now x is in radians for the trig part. The integral of cosine of x is sine of x. The integral of sine of x is negative cosine of x. And the integral of secant squared x dx is going to be tangent squared, or tangent x plus c. Okay. All right, so there's some rules right here. Multiplication by a constant, you can actually take that constant and move it out front. It's most preferable that you do that because sometimes you mess it up when you're working with the power rule. Okay, the power rule is right here when n does not equal -1, obviously, because if n equals -1, you're using the reciprocal rule. Okay, but it's going to be x to the n plus 1 divided by n plus 1 plus c. Alright, the sum rule, if you're doing the integral of two things being added, you just separate them and do the integrals of each. Okay, the difference rule, same thing. Integration by parts we'll learn later. We'll learn a little bit later. This is like the reverse chain rule, and substitution rule we'll learn a little bit later too. But that is pretty much it for it. We'll go over some examples. What is the integral of sine of x? It's going to be negative cosine of x plus c. Okay. What is the integral of x to the third dx? It's going to be one more, so we add 1 to here. Okay, we get that x to the fourth, and then we divide by it. Okay. Now, does that work with rational exponents? Yes, it does. So x square root of x is x to the 0.5, or 1/2. So we basically treat it as the power rule. So it becomes x to the 1.5 divided by 1.5 plus c. Okay. All right. Now, multiplication by a constant. What is the integral of 6x squared dx? We move the 6 out front, and then we just do the simple integration with x squared. Okay, and then we multiply by the 6, and we get 2x cubed. If you move the constants out front, they save you a whole headache later. Okay. All right. Sum rule. What is the integral of cosine of x plus x dx? Okay, you separate both parts and do the integral of cosine of x dx, and then add that with the cosine of x plus dx. And you get sine of x plus x squared over 2 plus c. Okay, same thing with subtraction, same rule. Okay. All right, now if we had to mix them all up, obviously we would just break it apart into each, let's say we had some difference in constant multiplication and power rules in here. Okay, we would separate them all into separate integrals. We would bring the constants out front. Okay, then we would do our actual integration of the powers, and then we would start doing the simplification. We would get 4z squared plus z to the fourth minus 2z to the third plus c. Okay. All right, and this is from mathisfun.com, really great website. If you ever just want to check out your just basic common rules for integration. Okay. That's it for us, and I'll talk to you guys later when we talk more about area. Bye.